Common emitter amplifiers. It seems to me that quite a few people sort of have some ideas about how to do common emitter amplifiers, but I'm not sure they've got all the ideas. So I'm going to tell you what I know, or at least what I think I know, and we'll see how it goes. So I'm going to show how we derive the gain for a common emitter amplifier, and then how we work out how to set the bias point, and then how to design around that. Now, there's just three things you need to remember about a transistor when considering a common emitter amplifier. So let's draw a transistor. Oh, look at that. And point one is that VBE is pretty much always equal to 0.7 volts. That's that voltage across there, 0.7. I'm not sure why that's coming out like a calligraphy thing, but there you go. Point two is that IC, which is the collector current, is pretty much the same as IE, the emitter current. And point three is that VCE, the collector emitter voltage, VCE, is equal to, we don't know. It can be anything. And what I mean by that is that the bias conditions don't dictate VCE. That's dictated some other way. And if you don't understand further what I mean, if you've ever looked at the characteristics of a transistor and you plot VCE against IC for various base currents, that's this here, you get these kind of characteristics where that's increasing base current. And you'll notice that for a given IC, let's choose this one here, the VCE value could be here, or it could be way over here. In other words, there's a huge range of acceptable VCEs for one collector current. And that's what I mean by point three there. Okay, so keeping those in mind, we've got enough to start analysing the basics of common emitter amplifiers. So let's shove that out of the way and we'll delve right in. Okay, so we've got some kind of supply voltage, a collector resistor, I'm doing an NPN device, an emitter resistor, and it's grounded, or ground, whatever you want to call it. And this is the voltage on the base, which is the input. This is the voltage on the collector, and that's the output. Okay, right, let's dig in and see what we can find. If you remember point one, VE is approximately equal to VBE. VE is approximately equal to VB minus 0.7 volts. Okay, so that means that VB is kind of reflected down here, but with an offset. Now, I should say that we are going to ignore DC offsets. We're only looking at the signal component, and then we'll go and put back in the DC stuff when it comes to biasing. That's a perfectly valid approach. But remember that VB is actually the input voltage, so we can say that VE is equal to Vin with an offset. Okay, that's great. So we know we've got Vin here. Now, if we focus on this device here, the emitter resistor, we now have the voltage across it, Vin, and of course we know its value, it's Re, so we can say the emitter current, IE, which is the current through that resistor, is equal to Vin over Re. Great. So we know the current going down here is Vin over Re. Super. Point three, the collector current is kind of inherited as being a copy of the emitter current, give or take, and is therefore also equal to Vin over Re. Great. That means the current going down here is Vin over Re. Now, when you want to work out what the collector voltage is, the way you have to do it is start off with a known set fixed voltage and calculate offsets along the way to the point you care about. So we start off at VCC and then we drop down to VC through whatever the voltage is across this resistor. So we can say 0.4 VC is equal to VCC minus the IR drop across RC. So that's IC RC. But you'll see from point 3 here we've got another expression for IC, and we've also got another DC term which we're going to drop. So VC equals minus this expression here, V in over RE times RC, or if you want to put it a slightly different way, is equal to minus V in RC over RE. Great. Now if you want to know the gain is out over in, right? And out is VC, and in is just V in as we called it. And if we drop in the expression for VC, we get minus V in RC over RE over V in. Cancel, cancel. So the gain is equal to minus RC over RE. Or if you prefer, it's just RC over RE, and it's inverting. So that's how we work out what the gain is. It's actually 3 stages cascaded. This part here is acting as an emitter follower that's replicating the input voltage down to this point here. This part here is acting as a transconductance amplifier. Its output is a current and its input is a voltage, so it has the units of transconductance, 1 over resistance. That's creating a current that whizzes all the way down this branch, and therefore the third block is this transresistance amplifier, which is taking as its input a current and producing a voltage. So it has the units of resistance, transresistance amplifier. So there's actually quite a lot to this, but the overall gain is simply the ratio, acknowledging the fact that the same current cascades all the way down here. So you've got that over that, and this is directly related to, linearly related to the input. So there you go, we now know that the gain is RC over RE. Great, but with a minus sign in front of it because of the inversion. Next step I'd like to look at is the output voltage range that you can have. And we're going to look at that by looking at a fully switched on transistor and a fully switched off transistor to demonstrate the extremes. So here we have RC, RE, whatever they may be, and I'm going to fully turn off this device by grounding the base. And then somewhere over here, a duplicate of the circuit with RC, oh, missed off RE, and this time we're going to fully turn it on. Probably wouldn't connect it quite like that in practice, but you get the idea. Okay, so if we focus on the off initially, if it's off, that means that there is 0 amps flowing through here because the transistor is absolutely wedged off, and there's also 0 amps flowing through here as well. And as a consequence of that, the IR drops across each of the resistors is I0 times RE equals 0, and there's also 0 volts drop across here. So in order to work out what the output voltage is, as before, we start off with VCC and we drop any voltage drops to get there, but there is no voltage drop, it's 0 volts. So in this case, this is at VCC, and by the way, the emitter is at 0 volts by the same logic. You start off at 0 volts and you go up 0 volts to get to this point. So looking at VCE, which is this voltage here, it's as big as it possibly can be. Now you can probably imagine, therefore, that as you begin to turn the transistor on, that must change in order for anything else to change in the circuit. So what happens is that the collector starts to drop down from VCC and the emitter starts to come up from 0 volts as you gradually increase the degree to which the transistor is turned on. So VCE kind of gets smaller and smaller and smaller as these voltages increase and squash the transistor in the middle. So the limiting case, when the transistor is as fully switched on as makes any sense, essentially there's 0 volts across here. It's not quite true, but it's a good approximation, in which case you can kind of ignore the transistor, because the same current is going down here, and you've got an RC there and an RE there, in which case the whole output from the point of view of VC now just looks like a resistive divider, a normal resistive divider. So in the case of fully switched on, the output is going to be VCC times RE over RE plus RC. Now I'm going to do some fiddling here and divide everything by RE, which is perfectly valid. Okay, and you'll see that becomes 1, that becomes 1, but this, RC over RE, ooh, that's the gain. Okay, so we can re-express this. The fully switched on case, the output voltage is going to be VCC times 1 over gain plus 1. Okay, that's pretty cool. So that means that there's a range of voltages that depend on the gain you configured it to be. 0 volts to VCC is the options available. In the off case, sure enough, the output voltage can be all the way up to VCC, as we discussed in the left-hand branch here. In the on case, this version here, it can get to VCC times 1 over gain plus 1, or if you prefer, just VCC over gain plus 1. This is the zone of possible output voltages. Okay, so you would probably argue that the best place to sit your unbiased output of VC, or that's not actually the right phrase, the biased output but with no signal on it, would be exactly halfway between its maximum and minimum, which is gain dependent. So somewhere here is where you kind of want it to be, and that's going to be the geometric average of this and this. So let's have a look and see what that is. On the one hand we've got VCC, and on the other hand we've got VCC over gain plus 1, and we're taking the average of those, so we're doing that. Now I could slightly reword that as VCC over 2 1 plus 1 over gain plus 1, or again I could put everything over gain plus 1 and say that's equal to VCC over 2 gain plus 1, so that's gain plus 2 over gain plus 1. This is your optimum bias point to allow the largest possible voltage swing output. Okay, so it's not by any means just VCC over 2. In the case that the gain is large, this will, as gain tends to infinity, the bracketed part here just tends to 1. But say you've got a gain of 1, which is much lower, then you've got 3 over 2 as the factor against half rail, which would be VCC over 2 times 3 over 2, which is equal to 3/4 of VCC. Now that makes sense if you think about it, because if you've got a gain of 1, then you've got R here, some sort of transistor, and R here. So whatever current you've got here is matched here when it's fully switched on. So the lowest that you can ever go is VCC over 2, and of course it can still go up to VCC. This is in the case of unity gain, where these values of resistor are equal. So the halfway point is halfway between VCC and VCC over 2. That's 3/4 VCC. Great. Okay, let's now look at piecing this all together and actually creating a circuit design using what we've constructed so far, when I've worked out how to steer this. Alright then, so let's set some design goals and we'll see how that goes. I don't know why this won't let me pan. Will you please let me pan? Thank you. Let's set some design goals. We'll have VCC equals 10 volts. We'll have gain equals times 5, or minus 5 if you like, because it's inverting. And we'll set the bias current, because why not, at 1 milliamp. Okay, brilliant. Right, this is on our design example. Design example. Okay. So we're going to start at the top and kind of work our way down, really. Let's just look. We just said we've got 10 volts here at RC. Remember I said I want 1 milliamp through it. There's not any great science there. And I want a gain of 5. So according to the magic expression here, gain plus 2 over gain plus 1. So the optimum point to plant this at without any signal VC here is going to be VCC over 2 times gain plus 2 over gain plus 1. So VCC over 2 is 5, and gain plus 2 is 7 over 6. Goody goody. Well, that's equal to 35 over 6, which in my estimation is almost exactly equal to 36 over 6, is equal to 6 volts. Close enough anyway. So we're going to try and plant this at 6 volts. Alright. That means that provided we've managed to bias things correctly, there will be 4 volts across here. That's the difference between the 10 volts and the 6 volts we want. So if we know we've got 4 volts across our resistor and 1 milliamp through the resistor, we've got R equals V over I, Ohm's law, and therefore RC in this case is going to be equal to that 4 volts divided by the 1 milliamp we've chosen, is equal to 4 kilo ohms. Great. 4K. 4K. We're getting somewhere. Now let's trundle down through the circuit a wee bit and focus on the next part, RE. Now remember, RC over RE is the gain, which we want to be equal to 5, and that's 4,000, the value we've already got, over question mark, RE. So if you jiggle that around, you'll see that RE equals 4,000 over 5 equals 800 ohms. Probably in reality you'd choose 820 or something like that. But that means that we've got 800 ohms there. Goody goody, we're making progress. Sorry, let's draw the ground lines in. Now we'll also have a milliamp coming down here. Remember, IC and IE are approximately the same. So that means that we now know the voltage on the emitter. VE is equal to IE times RE. It's just Ohm's law. IE is 1 milliamp because we said it is. RE is 800 ohms because we just said it is. So VE is equal to 0.8 volts. We can bang that in here. Let's choose a different colour. 0.8 volts. There. Great. Now, if we then go up a VBE, a 0.7, to get to the base value, VB, VB is equal to VE plus about 0.7 is equal to 1.5 volts. So that's the design goal here, is to try and squelch that to be 1.5 volts. Now you can cheat in terms of a simulation and just say that's 1.5 volts and see if you've managed to set up your 1 milliamp, or you can go through the aggro of setting up a resistor network here such that you've managed to achieve 1.5 volts here, and then capacitively couple in your circuit. So let's start off a little bit cheaty, and we'll just do the first method with the super bias, and we'll see if we've managed to calculate at least the bias point right, which sometimes takes 486 hours. No, I don't wish to update it. Put down one of those, put down one of those, another one of those. That one's going to be 4,000. That one's going to be 800. We want a supply of 10 volts, I think we said, didn't we? Well, where the hell did that go? Try again. Okay. That's 10 volts. Put some grounds on. Ground. My monitor's in 4K, which was a bit of a dumb move because you can't see anything. But work with me. Alright, that's just exactly what I wanted. Slick. Well done. Okay, luckily it's so small you can't actually see the idiotic mistakes I've made. And then the bias voltage, and we said that's about 1.5 volts. So we're going to give that 1.5 volts, which is a bit easier than bothering to work out the bias network. Okay, let's do a simulation command, DC operating point, simulation command. Always do it twice. I don't know why my mouse is being so jerky. Okay. Right. Mouse, behave. Run. Okie dokie. So you can see that we've got nearly 900 microamps. So yeah, I mean, I was guessing what VB would be here, so you'd probably tease that up a smidge to maybe 1.6, or probably that's probably too far. Okay, that's 1.02. 1.02, fantastic. Now you might be saying, well, hang on a minute, how do we know that this is actually doing the gain that you said? So let's do instead a transient simulation, so we can put a sine wave in. So we've got our 1.6 volts offset. I'll put in a relatively small 0.1 volts at 1000 hertz, and then we'll edit the simulation command and say we want to do a transient analysis up to 10e minus 3, that's 10 waves at 1000 hertz. Okay, so there's our input, and boop, there's our output. So hopefully you can see that we've got the gain that we wanted. And it's roughly biased at 6 volts, which was what I was aiming for, if you remember. So this is actually behaving quite well. We've got approximately the gain that we wanted. You can see the inversion. Let's go to a little bit of trouble to superimpose those a bit better on top of each other. There's two ways of doing that, cheating way and non-cheating way. Let's do the cheating way. Just see what the voltage was there. That's 5.914. So I'll numerically subtract that off, minus 5.914. That plonks that at 0. And we know the offset on this one, it's the DC offset we gave it. Minus 1.6, 1.6. The other version of minus. There we go. Right. So I asked for it to be 0.1 volts peak, and it's, okay, well, it's not quite 500 millivolts peak to peak, but it's not far off. So you get the idea. Obviously, if you wanted to create a bias network that would produce that 1.6, it's not too super hard, and away you go. So there it is, the basics of common emitter amplifier design that actually work. Who'd have thought it? Thank you for watching.